Students, can you able to hear me, students? Sorry for the delay. Can give me a reply in the chat box also. Like if my voice is lagging, please let me know. If it is clear, can anyone type like voice is clear? It is clear, huh? Okay, okay. Because I'm in the actually in the room, that's why I'm asking to the other like I'm using other network, Vodafone network. That is the reason I'm asking. Okay, okay. I'll mute others also. Today we'll start the 5th unit, tree data structure. Okay, you have started with what is tree, what are the different properties of tree, different types of tree. The same way you are going to study the what is graph. Okay, what actually it consists of, how it is modeled. Okay, obviously you are going to model the different cities into graph, right? You look at this green color, this right hand side um, diagram. You can model this each and every node as a city. Okay, let it be like Chennai, and this is Bangalore. Okay, you can model the city transport network as a graph. Okay, okay, Delhi like that. Okay, we don't need to bother about that. First, we have to know about what is a graph. So what again, it is a non-linear data structure. You know very about difference between linear and non-linear data structure. When they ask about non-linear data structure, you have to tell the examples like tree and graph. Okay, what actually is a graph? It consists of vertices. Vertice nothing but a circled one, no, that is called vertices. Okay, and edges, which is connecting between the two vertices. Two vertices is what? Edges. Okay, this is what edges. So what vertices and edges. The vertices other way you call as nodes. Okay, nodes or something else. Nodes. Right. A graph is an abstract data structure. Okay, that is used to implement mathematical concept of graph. A graph is often viewed as a generalization of the tree structure. Okay, I can tell that even a graph is the generalization of the tree structure. I can call tree is a graph. I can call tree is a graph. The difference between tree and the graph is that you can find a cycle in the graph, but in the tree you cannot find a cycle. It's not form any loop in the structure of the tree. That's why it's varied. But actually, tree is a kind of graph. Okay, any kind of complex relationship can exist between the vertices. That no, like why you are telling it's a complex relationship. There is some connectivity between these two vertices, right? There may be a complex relationship. Okay, that we don't need to bother about right now, right? According to the definition, and one more point I have to tell. If at any point, if my voice is not audible, please chat me in the chat box. Okay, type in the chat box so that let me know what is the status. That's what. So if I keep on speaking means that's not good. At any time, if my voice is lagging, please let me know. Okay. A graph is defined as the ordered set. So always you will define as an ordered set, nothing but V comma E. V's represent vertices and edges. Okay. The mathematical representation of graph is this one. G equal to U comma V. I hope you have studied in the what is that? Mathematics you are studying, no? You might have studied this graph very well, I know. So this is an example of graph. Okay, and this is a tree. You can easily find out that there is no loop. There's no loop in the tree. Okay. Next, why are graph useful? Okay, and nothing but where you are using. Okay, used to model any situation where entities or things are related to each other in pairs. See, you can tell that like it's not only meant for transportation network. Okay, we can model the transportation network as a graph. It's not like that. We can model our social network. You take any social networking like Twitter or Facebook, okay, Instagram. I can model the social network as a graph because each and every user in the Instagram, I call it as a node. Okay, and he is connected to a particular user is connected to some other users also, right? Nothing but he is with some relationship only, based upon the relationship only he is connected to some other users, right? So we can model the what even the online social network as a graph. Okay, and family trees. Okay, we can model the family tree as a graph also. Used to solve many real like problem. Graphs are used to represent networks. Yes, fine. So this is the application of graph. Okay, this is all basic theories only. Fine. Next is the example of graph. Right. When you observe this graph, when you observe this slide, you can at the bottom you can find two graphs. Okay, 1 and 2. Okay, here you can find that the edges, okay, the edges connecting between B and C are directed because it is having some arrow mark. There is only one way. There is no two-way communication between this what C and B. You can consider like that. It is a one-way communication between B and C. When you take any pair in this graph, it's a one-way communication because it is directed. I have drawn a arrow mark here. It is I like any information emerging from C, any information I want to pass, I can pass only to the B. Okay, right? When you look at this graph, okay, it's not directed. That we call it as an undirected graph. Okay, if it is not, there is no arrow mark, I call it as an undirected. Fine. So what is the use? So nothing but it's a two-way communication. I can communicate from A to B as well as B to A. It is possible because there is no direction. That's why it's termed as directed and undirected. Okay. And how will you represent the? One second. Okay. So when you take this graph, how will you represent the what vertices? See, this is the graphical representation of vertices. See, you have to note, not a graphical, mathematical representation of vertices in the graph G. Okay, and these are all the edges of the graph. Okay, this is the how I notate in the mathematical form. Okay, all these things you have to know about. These all basic things. Okay, how we will represent the or in the form of mathematical notation. Okay, what is graph terminology? Is nothing but what are the basic things you have to know in graph. That's what I termed it as graph terminology. Okay, when you take any node, or vertex, okay, there will be some neighbor, right? There will be some neighbor. If it is connected to the other person, it is called as a neighbor or adjacent nodes. Simple. Because these all things are useful in you'll next in the forthcoming slides. You will study about the adjacency list and adjacency matrix. Adjacency list and adjacency matrix, where you are going to represent the graph. For example, you take this one. How will you represent tree? It can be represented what either in array or linked list. Okay, when you take Q, it can be represented either in what array or linked list. The same way, if I want to represent in graph, if I want to represent the graph, okay, I can use either adjacency list or adjacency matrix. That will come in this forthcoming slide. Okay, where you will use the adjacency properties. Who are all the adjacent nodes to the particular node, or you got as a neighbor, and degree of a node. So degree is nothing but um, the edges emerging out of the node, or edges coming towards the node. Okay, we can call it as degree. That will show in the uh, next slide. Okay, degree is nothing but a node is emerging out. Sorry, an edge is emerging out of a particular node, or an edge is coming towards the node, is called as a degree. Okay, then what are the different types of graph? We take this one, regular graph. Okay, where each vertex has the same number of neighbors. Okay, when you take any neighbor, okay, for example, you can consider this undirected graph. Okay, so this is an undirected graph. I take a node 1. How many neighbors are there? 2 neighbors. When I take the node 2, how many neighbors are there? 2 neighbors. When I take the node 3, how many neighbors are there? 2 neighbors. So if it is like this, I call that type of graph is a what? A regular graph. I can call this as a graph also, no issues, right? I can call this as a graph. See, these two are not connected. 1, 2, 3. Okay. So there's no closed loop, that's all. But it is a graph. There are 3 nodes, there are 3 vertices in the graph. That's all. Even though it's not forming a loop, I call this as a graph. This is example of graph. These two are example of graph. Okay. Then what is path? A path P written as follows. Okay. If you want to reach from source to destination, if you want to reach from first node to the 10th node, I have to cross each and every vertices, right? For example, you are starting from Chennai to Delhi. You will cross via Bangalore, like Bhopal. You'll go towards like Agra, like you keep on going like that, right? So that's what each and every city is called as what? Vertices. That's what nothing but the path what I am following. Okay, that is the a path. Okay, path P written as P. So it is noted as P. Actually, this should be in all. This should be in suffix. Okay, V0, V1, all should be in suffix. Vn. Okay. Length n from a node u to v is defined as a sequence of n plus 1 nodes. Okay. Then simple path. Okay. It means that, for example, in a simple path, there will be only distinct vertices. There will be distinct vertices. A path P is known as a simple path if all the nodes in the path are distinct. Okay, it's not that I should not repeat the nodes. I should not repeat the nodes to reach the destination. Uh, if I go via a node 2, I should not come back again to node. Then I should not go to the 10th node. I mean the destination node. I should not come back to the uh, same node which I have visited already. Okay, that's what a simple path. The nodes should be distinct, with an exception that V naught may be equal to Vn. Why here nothing but, for example, I want to start from 1. I'm drawing here. Okay, there are many nodes. For example, there are many nodes. I want to start from 1 and I should reach the same 1. The destination my 1. My source is 1 and the destination is 1. So what will I do? I'll keep on visit like this. I might not visit this also, no issues. I'm visit and come back here. That's what V naught is the source and Vn is the destination. So both are same. That's what exception. The exception case is this: V naught may be equal to Vn, right? Then cycle. So cycle is nothing but a loop. Okay, a path in which the first and the last vertices are same. Okay, what I told, no, this one. This is forming a cycle, right? This is forming a cycle. So all this will be useful in applying the problem. Sorry, it will be useful in the application. And again, a simple cycle has no repeated edges. Okay. What is the simple path? What we said, no, the same thing. No repeated edges here. You have to note this point here. Okay. In case of simple path, there is no repeated vertices. In case of simple cycle, in case of simple cycle, no repeated edges. I should not use the same edge to reach the destination, except the first and last vertices. Okay, except the first and last vertices. Okay. Guys, can you able to follow me? Guys, can anyone give a reply? Because I keep on speaking. It's all about theory only. Just you have to know the basics. Sir. Once you know the basics, then we'll next move on to the um, kind of programming part also, like how it is represented in adjacency list, adjacency matrix. Anyhow, we might have studied this in mathematics, I think so. Yeah, I got a reply from few students. Yes, so could you brush up again path and simple path? Okay, okay. 1 second, I'll repeat the simple path and cycle. Okay. Once again, because one student has asked for doubt, I'll just 1 minute I'll explain. Then we'll move on to the next slide. Okay. For example, I'm having these nodes. Okay. If I start from one, if I want to start from one and reach the same one, I want to start from one and should reach the same one. Okay. What will I do? I'm start traversing from one. Okay. I may visit 2, 3, 4. There is a possibility of, if I want to, I should start from one and I should reach one. Sorry, erase this one. I start from one and I should reach one. Start from one and I should reach one. But what can I do? I can able to visit the same two. Same two. 1, 2, 2 to 3, 3 to 5, 3 to 2. It is also possible. Then I'll go to 1. This is not a simple path. Simple what? Path. Okay. I'll, I'll, just, I'll just open the presentation. Yes. So whatever I shown there, the path, it's not a simple path. Why? Because the node 2 is repeated. The node 2 is, I am again visiting the node 2. Okay. To reach a destination, I am visiting few nodes repeatedly and I reach the destination. That is called as a what? Path. That is called as a path, but it's not a simple path. A simple path is nothing but where there will not be repeated vertices. Okay, I hope you understand. Okay, and same like cycle. When you tell about cycle, if there's no repeated edges, okay, I got a reply. I think so. Yes. Okay. Thank you. Similarly, for cycle, instead of vertices, I am telling, instead of nodes, they are telling what? Edges. That's all. Simple. I'm just instead of nodes, there is no repeated edges. That is called simple cycle. Okay. Fine. Okay. Next, connected graph. Connected graph. 1 second. Sorry for the delay. Some external noise, that's why I muted myself. Okay. Next, we'll see the connected graph. Okay. So a graph is said to be connected if any two vertices in V, there's a path from U to V. So nothing but um, if any two vertices, a graph said to be connected for any two vertices, that you have to note down. For any two vertices, if I choose any two vertex in a node, either it can be 1, 10 or 5, 3, 7, 9, there will be a path. There should be a path. If there is a path, I can say it's a connected graph. It's a well connected graph. Okay, it means that I can reach from one node to any other node. That's what this means. That's what is a connected graph. Okay, if there is no possible to, if there is no possible to connect with any of the node, I can say it is not a connected graph. Okay, it's not a connected graph. That's all. And moreover, a connected graph that does not have any cycle is called a tree. Okay, therefore a tree is treated as a special graph. That's what I told. Okay, a tree is a special form of graph. That's all. That's the statement, final statement. Next, complete graph. A graph G is said to be complete if all its nodes are fully connected. Okay. For example, it means that like what actually there is a difference between complete graph and connected graph. Okay. For example, if you take any node. Okay. If I take any node, and if I want to reach 10, there will be a path. Okay. That type of uh, graph I call it as a complete graph. For example, see, there is a path from one node to every other node in a graph. Okay, the complete graph has n minus 1 2 edges. I'll tell the difference. I'll tell the difference. N into n minus 1 edges. Okay, 1 second. One second. Oh. A complete graph has n into n minus 1 uh, divided by 2 edges. Okay, where n is the number of nodes in the G. Right. So this I will explain this in when it comes to the complete graph. It means that, for example, this directed and undirected graph. Okay, when you take this directed and undirected, let me share here also. Take this one, directed and indirect. Um, okay, so these are the nodes. These are the nodes. Okay, since it is undirected graph, since it is undirected graph, if it is undirected graph, there is no what? Obviously, the edges will be reduced to half the size when compared to the directed edges. Okay, if you think of like it is directed, one can do what what is this? So I want to reach from 1 to 2, it's possible, but 2 to 1, how it is? It's not possible now. So I have to create another edge, right? I want to create another edge. I have to put this direction here like this. So this is like this. So if you so there is a difference between this and this directed and undirected. If it is undirected, the number of edges is reduced to half the size. But when you take this directed, okay, it increases the number of edges than the undirected graph. Okay, that's why it is n by 2. Okay, since they are using like uh, uh, undirected, it is n by 2. Okay, so since okay, let me share. Once you get into the next topic, you'll be clear also. So as of now, you know that a complete graph has this many edges. Okay, right. Labeled graph or weighted graph. Nothing but if you want to cover a distance, if you want to cover from city Bangalore to Delhi, okay, what is the distance? That is nothing but the weight or label. You are mentioning some, you are giving some identification to the edge. Okay, you are giving some identification to the edge. It can be either weight or label. Okay, that's what weighted graph. That's what assigned some data. Then multiple edges. What is here? Multiple edges, nothing but what I told. No, see, for example, you take here. Okay, distinct edges which connect the same endpoints are called multiple edges. Okay, that is, you can define like this. You can define like this. See, edge equal to u comma v. Okay, complementary to this also what u comma v. Right, that's what is the definition for multiple edges. Distinct edges which connect the same endpoints are called multiple edges. Next, loop. Okay, loop. So what is loop? An edge that has identical endpoints is called a loop. I'm starting from source, I'm starting from node 1 to reach the same node. That's why it is written as u. Identical nodes, u comma u. Okay, it can be self loop also. See, you can look at this graph. It is a multi graph. First diagram. It is a multi graph. A graph with multiple edges or loops is called multi graph. Okay, multiple edges. See, you can have a loop here, right? B. Again, visiting the, I'm starting from B and reaching the same B. That is called edge E4. I have assigned the label also, right? And you can find here also. So having multiple edges. Okay. Then what is size of a graph? The size of the graph is the total number of edges in it. Okay. Total number of edges. So like when you take this one, I can call this is tree or graph. Okay. Tree or graph. But how many size of this graph? 1, 2, 3, 4, 5. The size of the second graph or diagram is what? 5. Depends upon the number of edges in it. Fine. And this is the weighted graph. They are assigning some weights to the edges. It's what type of graph is this? Directed weighted graph. You have to note down. It's a directed weighted graph. This one, undirected graph. That simply you can call it as undirected or unweighted. Okay, undirected graph. Some simple. Next, we are going to see on directed graph. Right. A directed graph G, also known as a digraph. How we are calling the directed graph as digraph. Hereafter, we should call directed graph as digraph. Every edge has a direction assigned to it, as you know very well. What is out degree? Out degree is nothing but edges coming out. Okay, that are originating from at U. Okay, there are 5 edges originating from a particular node U. I call the out degree of the particular node is 5. Okay, originating. Okay, coming out. Fine, that is out degree. And in degree, similarly for in degree, right? So what are how many edges are coming towards a particular node is called the in degree. Towards the particular node, that is called in degree. Earlier you studied only the degree of a node. When you call degree, I can combine it, no problem. but here again splitting out degree and in degree. Next, isolated vertex. A vertex with degree 0. Okay, such a vertex not an such a vertex is not an ending point of any edge. See, I can have like this also. This one. See, I am drawing a graph now. Okay, I'm drawing a graph now. See, I will call this entire nodes is a graph. See, when you look at this node, it's not connected to the any of the node, but it is part of the graph. It is part of the graph, but it is divided into two components. The graph is divided into two components. Okay, first component is I can tell that this is the one component. The second component is this one. Okay, the node which is isolated here is nothing but the isolated vertex. Okay, isolated vertex. And what is pendant? Nothing but vertex with only 1 degree. Degree is 1. I call it as an pendant vertex. Then cut vertex. Okay, if I delete any one of the vertex in the graph, okay, it automatically what happens? It creates a vertex which when deleted would disconnect the remaining graph. Okay, if I delete any in the middle of the graph, if it possible to if it makes the graph into two component, I call that vertex a cut vertex. Okay, okay. What I'm doing, see, like this the graph is there. Now 1 2 3 4 5. Okay, if I delete this 3 vertex 3, what automatically happens? This 1 and 2 become a separate component, and 4 and 5 will become separate component. So that's what it's a kind of intermediate node which connects the it's become a bridge, right? It is acting like a bridge. That's what, nothing but the cut vertex. I call this number 3 vertex is a cut vertex. And source, okay, where I'm starting positive out degree, okay. Then sink, a node U is known as a sink if it has a positive in degree but a 0 out degree, vice versa. Okay, source and sink, a node U is known as sink if it has a positive in degree, right? A node can have 5 uh, edges, in degree edges, but 0 out degree. That type of node I call it as sink, right? Okay, so I hope I can directed draft still is not over. Shall we end the class here, guys? Still 5 minutes. So, if you have any doubt in this, please let me know. So, what is the other thing? So, as we are discussing about this graph, no digraph, strongly connected directed graph. Okay, strongly connected, weakly connected. You have to note on this point. Okay, a digraph is said to be strongly connected if only if there exists a path between every pair. If you take any pair, there will be a path. Okay, considering that that type of graph, that graph is what directed graph, that you have to note down. In a directed graph, if you take any pair of nodes, any pair of vertices, there will be a what? There will be a possibility of reaching the other node. Okay, okay, source and destination, right? If pair nothing but a source and destination, when you pick any node, so that's why I call this as strongly connected, and weakly connected. So I'll mention here. That's what that is. If there is a path from node U to V, obviously there will be a path from V to U. Okay, but there may be a possibility that there won't be path path from B to U. There won't be path from B to U. Okay, if it is like, no, it's not a strongly connected graph. Okay, that way you have to keep in mind, like we are dealing with a directed graph. Always directed graph takes extra edges. That's one of the disadvantage in the directed graph. Extra edges. And weakly connected graph. A directed graph is said to be weakly connected if it is connected by ignoring the direction of edges. Nothing but what? There's no what ignoring the edges direction, right? Then it is considered as the weakly connected digraph. And what about this multiple edges we have seen? No, distinct edges which connect the same endpoints are called multiple edges, right? Distinct edges which connect the same endpoints. And simple directed graph. A directed graph is G is said to be simple direct graph if it has no parallel edges. If it has no parallel edges. For example, okay, see, it will not happen like this. There's no multiple edges. If it is no multiple edges, then I call what? It is a simple directed graph. Okay, I'll complete this with this slide. Next, biconnected component. A vertex V of G is called an articulation point if removing V along with the edge results in a graph that has at least two connected component. Okay, that's what we told. No, like cut vertex. We discussed about the cut vertex, right? So that vertex is called an articulation point. That if you remove that V, if you remove that V along with the edges, it means that along with the edges in the sense, like what are the edges connected to the particular cut vertex? Okay, what are the edges? All the edges connected to the, or here you're telling the incident on V, or not even incident on the cut vertex. It leads to two connected components. Leads to two connected components. That type of vertex I call it as an articulation point. If it does not does, okay, even though if I if there is like if there is no articulation vertices, then I call that graph is a biconnected graph. Okay, a simple example for biconnected graph is this one. If I remove any vertex here, it's not affecting the other vector. It's not like creating uh, two components, right? Even if like what it said, like at least two connected, maybe 2, 3, 4, like it may be. It depends upon the network formed, right? Why? Because um, when you take in your class, okay, you take in your class. In your class, all the information are disseminated through your class representative. Okay, if I try to hide the particular vertex or the representative, what happens? Obviously, you cannot like what you cannot get information, right? You can assume like that, right? So there is a possibility of division of many number of components, connected components, right? So there, if there is no articulation vertices, then that type of graph is said to be biconnected graph. The example is here. And understand about this biconnected graph? Can anyone reply? Understand about this biconnected graph? What is articulation point? Articulation point is nothing but when you remove the edge. If you remove the, what is it? Vertex along with the edges, it has to create different connected components. If it's so, it is not a biconnected component. If it's so, it's not a biconnected component. If I remove that articulation vertex again nothing but a vertex which is having like a vertex which you are removing along with the edges will not create a different component, two different minimum or two different components. Okay, guys, is it fine? Guys, can you hear me? Yes, okay. Okay, shall we end the class, guys? Can anyone reply? Please, I need some more reply. Okay, okay, thank you, guys.